If you love flying as much as I do, your priority will always be getting that window seat. Some of my favourite experiences from travelling have been experienced through the window of a plane, from looking down on the Burj Khalifa to returning to the green fields of Ireland. Flying has always been a special experience for me, so when I got a chance to fly in the Boeing 787 Dreamliner with its huge windows, I was extremely excited. I'd been waiting for years to get the opportunity to fly in this groundbreaking plane. To some of you, it may just look like another everyday passenger plane, but the 787 is a revolutionary plane. The Dreamliner was the first commercial passenger plane to fly with the majority of its structure being built with composite materials, mostly carbon reinforced plastics. This reduced the weight of the aircraft dramatically, helping it be around 20% more fuel efficient than a similar sized aircraft. That 20% increase in fuel efficiency isn't just saving you and the airline money, but it has allowed new flight routes that were previously financially unviable to open. You see, the 787 is not a huge plane. It can carry less than half the passengers than the double-decker Airbus A380 and fills the size gap between the long-range Boeing 777 and the short to mid-range 737. Boeing specifically built this plane to serve more niche routes that larger planes could not serve, as the amount of people flying between the locations was too low to sell the number of tickets needed to make it profitable. Airlines call these long, thin routes. Want to fly from Dublin to Los Angeles directly? The 787 made that possible. No more stopping in London or New York. This ability may have even saved Polish airlines from bankruptcy, as the Dreamliner finally allowed them to profitably fly directly from their Warsaw hub to New York, Chicago, and Toronto. This is great for airlines and great for any of us who live in relatively small cities that usually have to travel to the nearest large airport to fly to our final destination. But my favourite thing about the Boeing 787 are those huge windows. The 787's windows are this much larger than an average airplane window. If you're anything like me, you will always end up with your face crammed next to the window trying to get the best view possible. But with the 787, you can see so much while sitting back and relaxing. It really gives you this wonderful panoramic view feeling. It also has these electronic dimmers, which do away with the need for those crappy plastic shutters that people insist on opening while others are trying to sleep. That isn't possible with the 787, as the master dimming switch is controlled by the flight attendants. So you may be wondering, why are these windows so much larger than other planes? This is another advantage of composite materials. You may remember from my first video, early passenger planes, like the de Havilland Comet, had a series of unfortunate mid-air explosions. After intensive research, the investigators discovered that the square windows were blocking the flow of stress in the structure, making it pile up in the corners of the window. Round windows allowed the stress to flow much more smoothly around the windows, and thus our windows have been rounded ever since. But the shape is not the only thing that can elevate stress concentrations. The size of the window has a huge effect on it too. A larger window means more stress has to detour around the window, and thus the stress concentration is elevated, which can result in cracks and failures. So these large windows do result in higher levels of stress concentration around the 787 windows. But I failed to mention one factor in that short little 2-minute video a year ago: fatigue. Over the course of a plane's life, it is repeatedly pressurized and unpressurized as it rises and falls through the atmosphere. This means the material experiences varying stresses continually over its life that can damage it. This was the second piece of the puzzle for the de Havilland Comet mystery, and its engineers proved it by building this huge water tank where pressurization tests could be done quickly. The test fuselage had undergone 1,230 normal flights and 1,830 tank flights before it failed at the corner of the square windows. This is why parts need to be replaced after years of use. A part may handle a single application of a load without any problem, but after many cycles of loading, the material will begin to weaken as tiny cracks form in the metallic structure. Metals like aluminium, which is traditionally used for aircraft fuselage, have a natural tendency to form cracks over time. This is because small defects in the crystal structure, called dislocations, which are essentially holes in the atomic structure, create weakness that makes it easier to deform. These dislocations can travel through the metal structure and have a tendency to coalesce, and so after hundreds of cycles, what was once a small defect can grow into a large defect in the form of a crack, and these cracks cause failure of the part. Fatigue failure in composite materials is incredibly complex, and we still have a lot to learn about the subject. I have no problem admitting right now I don't understand it enough to teach any of you with confidence on the details, and I have a thesis specializing in the subject. But I can say this with confidence: fatigue failure does not happen as quickly in carbon fibre reinforced fuselages, and there are many tests to prove that. The 787 fuselage is manufactured by wrapping layer after layer of resin-soaked carbon fibre around the fuselage many times. This creates a structure that is very resistant to fatigue, as the high-strength fibres are wrapped continuously around the fuselage. Fatigue failure will eventually occur in the plastic resin holding the fibres together, but it takes a great deal longer than in aluminium. This allows the carbon-reinforced plastic frame of the 787 to tolerate higher stresses in the fuselage and last longer doing it. There is still a lot to be learned about the mechanics of composite materials. Composite materials are a difficult material to work with at the best of times, and we will be learning more about that in the next video, where we will be learning more about the history of the material, and I will be visiting a local composite factory to show you more about the manufacturing process. Thanks for watching. This episode is brought to you by Squarespace, who have helped me make my next move with my website. One of my big goals for this year is to finally create the beautiful website that I envisioned when I first started this project. I am in the process of relaunching the Real Engineering website and will be continually improving it over the next year, and will be able to share my progress at the end of videos thanks to Squarespace. Squarespace allows you to create a beautiful website or online store with award-winning templates. They have 24/7 customer service, and their intuitive design platform makes it easy to create the website you dreamed of. You can make your next move with Squarespace and build a beautiful website by using the code REALENGINEERING for 10% off your next purchase. Thank you, Squarespace, for helping Real Engineering exist both here on YouTube and on our beautiful new website. And thank you all to my viewers and Patreon supporters too. One of my Patreon supporters actually reached out to help me build this site. Being able to interact with you all there has been amazing, and the feedback you give me on early drafts of my videos is priceless. Thank you. Last week I introduced a new reward in the form of the Real Engineering Geartooth logo t-shirt, which you can get on Patreon or over at dftpa.com. If you'd like to see more from me, the links for my Patreon, Facebook, Twitter and Instagram accounts are in the description.